Our cosmic backyard hides forces that could rewrite the laws of physics. We are setting out on a journey across the Virgo Supercluster to uncover 25 of its deepest mysteries. By the end, you will grasp the profound secrets lurking in the darkness between galaxies. We will confront a colossal gravity anomaly pulling us toward the unknown and encounter ghostly galaxies made almost entirely of invisible matter. What single cosmic question keeps you gazing at the night sky? Our very motion through the cosmos is being steered by a hidden force. The first of our great mysteries is known as the Great Attractor, a colossal source of gravity so immense it is pulling our entire Milky Way galaxy and thousands of others toward an unseen point in the void. This mysterious region lies approximately 250 million light-years away, hidden within the Norma cluster, yet for all its power we cannot see it directly. Our view is blocked by the thick dust and brilliant stars of our own galaxy's central bulge, a region astronomers call the zone of avoidance. It is like trying to see a distant city through a dense, permanent fog. So what could possibly exert such a powerful gravitational pull? Some theories suggest it is simply a massive, dense cluster of galaxies, one of the largest structures in our local universe. But the sheer scale of the attraction has led others to propose more exotic possibilities. Could it be a concentration of dark matter of unimaginable proportions, or perhaps a cosmic structure we do not yet have the physics to describe? This unseen engine of motion reminds us that the true rulers of the supercluster may be the things we cannot see at all. Even as a hidden force pulls us through the cosmos, other structures reveal the profound influence of the unseen. At the very heart of the Virgo cluster lies a true giant, the galaxy Messier 87. This supermassive galaxy dominates its surroundings, but its visible stars are merely the tip of a colossal, invisible iceberg. Surrounding Messier 87 is a halo of dark matter so immense and so puzzling that it forces us to question everything we think we know about this elusive substance. We can measure this halo not by seeing it, but by observing how its immense gravity warps the very fabric of space around it. This effect, called gravitational lensing, acts like a cosmic magnifying glass. When light from a more distant galaxy passes near Messier 87, its path is bent and distorted by the halo's gravitational field. By carefully mapping these distortions, astronomers can trace the outline of the invisible mass causing them. The results are staggering. The dark matter halo enveloping Messier 87 is not only vast, it is also shaped in ways that our best models struggle to explain. It seems to be far more spread out, and its density changes in unexpected patterns compared to what simulations of galaxy formation predict. Why does this matter? This is not just about one galaxy. Messier 87 serves as a cosmic laboratory. If our understanding of dark matter is correct, its behavior in such a massive and well-studied system should be predictable. The fact that it is not suggests that dark matter might be more complex than a simple, passive gravitational glue. Could it be that dark matter particles interact with each other through some unknown force? Or does this immense halo point to a different type of dark matter altogether, one with unique properties we have yet to imagine? The ghostly halo of Messier 87 does not just hide a galaxy, it guards a fundamental secret of the universe. But dark matter is not the only substance playing a game of cosmic hide and seek. Our inventory of the universe itself seems to be incomplete. According to our most trusted measurements of the early universe, we know precisely how much ordinary matter, the stuff that makes up stars, planets, and you and me, should exist today. Yet when astronomers tally it all up within colossal structures like the Virgo cluster, a significant portion is simply missing. This is the mystery of the missing baryons. Baryons are simply the particles that constitute all the tangible things we see. Think of the universe's budget for normal matter, the blueprint imprinted in the cosmic microwave background radiation. tells us exactly how much should have been created. But when we count the galaxies, the stars, and the dust within the Virgo cluster, the numbers fall drastically short. So where did it all go? The leading suspect is a vast, diffuse web of incredibly hot gas. This is not a gas you could ever breathe. It is a superheated plasma with temperatures soaring into the millions of degrees, so hot it only reveals itself in the most energetic X-ray light. This filamentary gas is thought to weave through the immense voids between galaxies in the supercluster, a faint and ghostly architecture. Finding it, however, is a monumental challenge. Its extreme temperature means it glows not in visible light, but in low-energy X-rays that are incredibly difficult to detect. It is like trying to spot the heat haze rising from a single candle from miles away. The hunt for these missing baryons is more than just cosmic accounting. It is a fundamental test of our understanding of how the universe assembled itself. If we cannot find this matter in the places our models predict it should be, then we may have to reconsider how the great cosmic structures formed and evolved. The answer is likely hiding in plain sight, woven into the very fabric of the space between the stars. And while we search for the universe's missing matter, some galaxies reveal a reality where darkness has already won. Tucked away in the constellation Coma Berenices lies one of the most enigmatic objects ever discovered, the galaxy Dragonfly 44. At first glance, it is a cosmic ghost, a wispy, ethereal smudge so faint it was only identified in 2015. But its appearance is a profound deception. Measurements of the motions of its stars reveal a shocking truth. Dragonfly 44 possesses a mass comparable to our own Milky Way, a colossal amount of material. Yet it emits a mere 1% of our galaxy's light. This means that for every pinprick of starlight we can see, there is 100 times more mass in a form we cannot see. This galaxy is almost entirely composed of dark matter. The puzzle is not just its existence, but its failure. How did a galaxy with all the gravitational potential of the Milky Way end up with so few stars? The leading theory suggests it is a failed giant. Billions of years ago, it may have been brimming with the gas needed to birth stars, but something prevented that process from taking off. Perhaps it was situated in a harsh environment within the Coma cluster, where gravitational tides from neighboring galaxies ripped away its gas or heated it so much it could not cool and collapse. Or maybe its own dark matter halo was structured in a way that stifled star formation from the very beginning, creating a gravitational landscape where gas simply could not coalesce. Dragonfly 44 stands as a fossil from the early universe, a relic of a path not taken. It forces us to ask a difficult question. Is our own bright, star-filled Milky Way the rule for galaxy formation, or is it the exception? In the vast, dark reaches of the supercluster, silent, ghostly giants like this one might be far more common than we ever suspected. There is a galaxy so perfectly structured it seems almost artificial. Drifting through the vast expanse, Hoag's object presents itself as a cosmic bullseye, a near-flawless ring of brilliant blue stars encircling a central core of older yellow stars. Between these two distinct stellar populations lies a profound and seemingly empty gap, a dark void that cleanly separates the young from the old. This celestial rarity defies the common image of a spiral or elliptical galaxy, standing instead as a pristine island of order. How could such a perfectly symmetrical object form? The most intuitive theory points to a violent past, a direct collision where a smaller galaxy pierced the heart of a larger 1 billion years ago. The gravitational shockwaves from such an event could have rippled outward, compressing gas and triggering a firestorm of star formation in a perfect ring, while leaving the central core relatively undisturbed. Yet, there is no obvious culprit, no galactic remnant left behind to blame for this act of cosmic vandalism. Another possibility involves a more subtle process known as resonance, where the galaxy's own gravitational field creates stable orbits at certain distances, like the harmonic notes on a vibrating string. Gas and dust could have naturally gathered in this resonant ring, collapsing into stars while the regions inside and outside were swept clean. But this too struggles to explain the sheer perfection and isolation of the ring. Hoag's object remains a profound enigma, a single, elegant question mark hanging in the dark. It challenges our assumptions about galactic evolution, suggesting that the paths to structure in the universe are far more varied and mysterious than we ever conceived. While some structures in the cosmos exhibit stunning perfection, others present us with profound emptiness. Near the bustling Fornax cluster of galaxies, astronomers have mapped a vast and unsettling region of space known as the Fornax void. This is not a simple, small gap. It is a colossal spherical emptiness, a bubble in the cosmic web so large and so devoid of galaxies that it defies our standard models of how the universe arranged itself after the Big Bang. According to our understanding, matter should be distributed in a relatively even web-like pattern, with filaments connecting dense clusters and leaving smaller, more predictable voids. The Fornax void, however, is an anomaly. It is far emptier than it should be, a true cosmic desert whose existence suggests that the processes which sculpted the large-scale structure of our supercluster may have been more violent or more random than we ever imagined. What could have cleared out such an immense volume of space? Perhaps a powerful, ancient force pushed the matter away, leaving behind a legacy of nothing. This void is a silent challenge to our maps of the cosmos, a reminder that the gaps between the lights can be just as mysterious as the lights themselves. Not all cosmic mysteries are defined by their emptiness, however. Some are defined by what they stubbornly refuse to become. Drifting between two massive galaxies in the constellation, Leo hangs one of the largest and most primordial structures ever observed, the Leo ring. This is a gigantic, loop-like cloud of cool hydrogen gas, so vast it could easily form billions of stars. Yet it has not. This ancient ring of raw material simply orbits the two galaxies, a silent and pristine relic from the early universe. Its very existence is a puzzle. How did this massive cloud of gas survive for billions of years without collapsing under its own gravity to ignite a firestorm of new stars? One compelling theory suggests it is a fossil from a direct collision between its two parent galaxies, a splash of primordial gas thrown out into intergalactic space during a violent cosmic merger. Another, even more intriguing idea posits that the Leo ring is a leftover building block from the formation of the supercluster itself, a surviving pocket of the primordial gas cloud that first gave birth to all the galaxies in this region. Its refusal to form stars is its greatest secret. The cloud may be too diffuse, its internal motions too turbulent, or it may be shielded from the shockwaves that normally trigger star formation. The Leo ring is a cosmic museum piece, a frozen moment in time that holds the untapped potential for an entire galaxy, waiting in the dark for a trigger that may never come. Deep within the cosmic static, whispers from the void defy all explanation. Among the newest and most baffling of these signals are odd radio circles, or ORCs. One such enigma, ORCJ0102-2450, was discovered within the Virgo Supercluster. These are not points of light, but colossal rings of radio emission so vast they could engulf entire galaxies. They appear out of nowhere, ghostly halos hanging in space with no visible source to power them. They are not remnants of supernovas, and they do not correspond to any known objects in other wavelengths of light. They are simply there, immense and silent. Could they be the shock waves from a truly gargantuan event, the echo of a merger between supermassive black holes? Or are they the throats of cosmic wormholes predicted by theory but never seen? For now, ORCJ0102-2450 is a perfect circle of mystery, a question written in radio waves across the sky. Far from these silent rings, other signals are startlingly brief and impossibly powerful. Fast radio bursts are the universe's most dramatic flashes in the pan. In a fraction of a second, a single FRB can release more energy than our Sun emits in 80 years. While most come from billions of light years away, one was recently pinpointed to a startlingly familiar location, a galaxy known as M81, one of our nearest cosmic neighbors in the supercluster. This proximity shatters many of our best theories. The leading model for these bursts involves magnetars, the highly magnetized corpses of dead stars. But the FRB in M81 originated from a globular cluster, a dense swarm of very old stars where magnetars are not supposed to form. This single burst from next door forces a complete rethink. If it was not a magnetar, what could possibly generate such a concentrated, titanic blast of energy? The answer may lie with an exotic object we have not yet considered, or perhaps it reveals a new, more violent phase in the life of ancient stellar systems. The M81 burst is a stark reminder that the universe's most energetic phenomena can ignite uncomfortably close to home. Beyond these brief, brilliant flashes, the cosmos also hums with a persistent, low-frequency song. Stretching across an unfathomable volume of space, the Perseus-Pisces supercluster is enveloped by a faint but enormous radio halo. This is not a localized source, but a diffuse ocean of radio emission, a testament to energetic processes working on the very largest scales. The sheer size of this halo is the first puzzle. What could possibly accelerate electrons to near light speed across such a vast expanse? The leading suspect is turbulence, generated as galaxies move through the supercluster's hot gas, or perhaps by the gentle, continuous inflow of intergalactic material. But the mechanisms are not fully understood. This faint glow is the signature of a dynamic, churning ecosystem, where gravitational forces and magnetic fields interact in a complex cosmic dance. It is a subtle background hum that speaks of the immense energy flowing through the seemingly empty spaces between the clusters, a permanent signature of the supercluster's restless, ongoing evolution. Some galactic cores hide secrets that time forgot. Nestled within the Perseus cluster, the galaxy NGC 1277 appears utterly ordinary, a lenticular island of ancient stars. Yet at its silent heart lies a gravitational monster of truly staggering proportions, a supermassive black hole that defies all expectations. This is not merely a large black hole, it is a relic, a cosmic fossil preserved from the dawn of time. Its mass has been measured at a breathtaking 17 billion times that of our own Sun, a figure so immense it comprises a staggering 14% of the entire galaxy's bulge mass. To put that into perspective, the supermassive black hole at the center of our own Milky Way makes up less than 1% of our galactic bulge. This disparity is not just a curiosity, it is a direct challenge to everything we thought we knew about how galaxies and their central black holes grow together. For decades, the prevailing model has been one of co-evolution. A galaxy and its central black hole grow in tandem, feeding on gas and merging with other systems. The black hole's growth is self-regulating, with intense radiation from its feeding periods blowing away surrounding gas and ultimately shutting off its own fuel supply. This process creates a predictable, tight correlation between the mass of a galaxy's central bulge and the mass of its black hole. NGC 1277 shatters that correlation. Its black hole is not just overweight, it is impossibly so, a behemoth from an era when the rules were clearly different. How did this happen? The leading theory suggests that this black hole was born in the universe's chaotic infancy, forming directly from the collapse of a gigantic cloud of primordial gas. This is a different genesis story from the slow, steady growth we see elsewhere. After its formation, the galaxy around it simply stopped evolving. It experienced no major mergers for billions of years. Its gas supply was somehow cut off and its stars aged in isolation. The black hole, with nothing left to feed on, became dormant, a sleeping giant frozen in time. This makes NGC 1277 a unique time capsule. It is a snapshot of the early universe, a galaxy that somehow avoided the constant churn of cosmic evolution that shaped all its neighbors. Its existence forces a profound question. Were these monster primordial black holes once common, with most later being buried or reshaped by galactic mergers? If so, then this silent, ancient galaxy is not an outlier but a rare survivor, showing us a forgotten path in the history of cosmic structure. Just when we thought we understood the cosmic rulebook, a galaxy broke all the rules. NGC 1052 DF2 drifted into view as a cosmic ghost, a diffuse smudge of stars so sparse you could almost see right through it to the galaxies beyond. Initial observations suggested it was just another ultra-diffuse galaxy, similar to Dragonfly 44, a place where dark matter reigned supreme. But when astronomers measured the motions of its star clusters, they were met with sheer disbelief. The clusters were moving far too slowly. Their gentle, placid orbits indicated a gravitational pull so weak that the galaxy's total mass was almost exactly equal to the mass of its visible stars. There was no room left for dark matter. This finding sent shockwaves through the world of astronomy. For decades, the existence of dark matter was the cornerstone of our understanding of gravity and cosmic structure. We believed it was the invisible scaffolding upon which all galaxies were built. NGC 1052 DF2 was not just an outlier, it was a direct contradiction. It was a galaxy that had somehow formed and survived without the gravitational anchor we thought was absolutely essential. The immediate reaction was one of profound skepticism. Could our measurements be wrong? Was the galaxy simply positioned in a way that fooled our instruments? Yet repeated studies confirmed the initial result. This was not a measurement error, it was a genuine cosmic anomaly. The discovery forced astronomers into a difficult position. If dark matter is a real substance that can be separated from ordinary matter, then how did this galaxy lose it all? One theory suggests a violent past. Perhaps NGC 1052 DF2 was once a normal galaxy that had a catastrophic encounter with a much larger neighbor. The gravitational tides from that interaction could have violently stripped away both its dark matter and much of its gas, leaving behind a skeleton of stars. This would make it a cosmic plunder victim, a galaxy robbed of its most fundamental component. The existence of such an object, however, cuts both ways. For proponents of modified theories of gravity, who argue that dark matter does not exist and that our laws of gravity are simply incomplete, NGC 1052 DF2 was initially seen as a triumph. Their models, which adjust how gravity works on large scales, did not require any dark matter to explain galaxy rotation, but the triumph was short-lived. The problem is that these alternative gravity theories struggle mightily to explain all the other evidence for dark matter, such as the gravitational lensing we see in massive clusters. Furthermore, if you tweak gravity to explain why NGC 1052 DF2 has no dark matter, you then break your explanation for all the other galaxies that clearly do have it. This galaxy did not solve the dark matter debate. It instead deepened the mystery, presenting a paradox that neither side could fully resolve. It proves that dark matter is not just a simple ingredient you mix into every galaxy. It is something that can be present or absent, and its relationship with visible matter is far more complex and nuanced than we ever imagined. NGC 1052 DF2 stands as a profound challenge, a galaxy that by all rights should not exist, forcing us to question the very foundations of our cosmic models. Even in the final act of a star's life, nature can produce structures of breathtaking precision. Far from the chaotic collisions of galaxies, a dying star in the constellation Monoceros has crafted one of the most geometrically perfect forms known to astronomy, the Red Rectangle Nebula. This is not a fuzzy cloud or a ragged shell, but a stunning bipolar nebula that appears from our vantage point as a near-perfect rectangle of deep crimson light, complete with a distinct X-pattern of rungs that resembles a celestial ladder. The source is a binary star system where a dying red giant star is shedding its outer layers. The gravitational influence of its companion star is thought to funnel this expelled material into two opposing cones, and because we are looking at these cones almost directly from the side, they form the illusion of a sharp-edged rectangle. But the true mystery is not its shape, it is its color. The nebula glows with an intense and unexplained red light, a phenomenon astronomers call extended red emission. This is not the simple red glow of hydrogen gas common in many nebulae. This is something far more strange and specific. The leading theory points to complex organic molecules known as polycyclic aromatic hydrocarbons. These are essentially large, flat molecules made of carbon and hydrogen, akin to tiny flakes of soot. When illuminated by the ultraviolet light from the central stars, these molecules are thought to fluoresce, producing that characteristic red glow. Yet, the exact chemical process remains elusive. Laboratory experiments have struggled to perfectly replicate the specific shade and intensity of the red emission we observe. Are we seeing a unique form of carbon dust, or could even more complex molecules, potential building blocks of life, be responsible for this cosmic artwork? The red rectangle is more than a beautiful farewell. It is a chemical laboratory on an unimaginable scale, its precise geometry hiding a recipe of cosmic chemistry we have only just begun to decipher. The universe's largest structures are not the brilliant clusters of galaxies, but the profound emptiness between them. Bordering our supercluster lies a region of such staggering nothingness it has earned the name the Boötes Void, one of the largest known cavities in the entire cosmos. Imagine a spherical volume of space nearly 330 million light-years across. Within this unimaginable vastness, you would expect to find thousands, perhaps even tens of thousands of galaxies. Yet astronomers have counted only 60. The emptiness here is not just a simple gap, it is a cosmic chasm of almost incomprehensible scale. If our own Milky Way were placed at its center, we would have lived in total isolation, with no knowledge of other galaxies until the 1920s. This profound void presents a direct challenge to a fundamental pillar of modern cosmology, the cosmological principle. This principle states that on a large enough scale, the universe should look roughly the same in every direction, a uniform tapestry of matter and energy. The Boötes Void is not uniform. It is a glaring anomaly, a desert so vast it seems to defy the very rules of cosmic structure formation. What could have caused such an immense region to be swept so clean? One theory posits that the void is not truly empty, but is instead filled with dark matter, the invisible scaffolding of the cosmos, with ordinary matter simply failing to condense there. Another, more dramatic idea suggests that the Boötes Void is the result of a merger of smaller voids, a cosmic bubble that grew to an extreme size over billions of years. Yet even these explanations feel inadequate for an emptiness of this magnitude. The void stands as a silent question, forcing us to wonder if our understanding of the universe's largest scale structure is truly complete, or if we are merely mapping the shore of an infinite ocean of mystery. This relentless cosmic expansion is governed by a force far more mysterious than gravity. While we have been exploring the structures within the Virgo Supercluster, a deeper and more powerful influence is already at work, slowly tearing the cosmic web apart. This is the pervasive effect of dark energy, the enigmatic driver of the universe's accelerating expansion. Its influence is not a distant future event. It is a process happening right now, subtly reshaping the destiny of every galaxy cluster we see. On the grandest scales, dark energy acts as a form of cosmic repulsion, counteracting the inward pull of gravity that has built these immense structures over billions of years. Within the Virgo Supercluster, this means the delicate gravitational bonds that hold galaxy clusters together are being steadily, inexorably stretched. The space between individual galaxies within a cluster is still dominated by gravity, holding them firmly together for now. But the vast filaments of the cosmic web, the bridges that connect one cluster to another, are under assault. Over trillions of years, this relentless expansion will pull these filaments thin, eventually severing the connections between galaxy clusters entirely. The supercluster will not fly apart violently, but rather fade into isolation, its constituent groups and clusters becoming isolated islands in an ever-darkening and ever more empty sea of space. The ultimate fate of this grand structure is to dissipate, its components losing their cosmic context forever. And yet, for all its profound consequences, we know almost nothing about what dark energy actually is. Is it a constant property of empty space itself, as Albert Einstein once proposed with his cosmological constant? Or is it a dynamic energy field that has changed over the life of the universe? Every observation we make of the supercluster's large-scale motion and structure is, in part, a measurement of this shadowy force's grip on reality. It is the greatest unsolved problem in physics, and its answer is written in the slow, silent drift of every galaxy in the sky. Its iconic brim and central bulge make the Sombrero Galaxy one of the most recognizable island universes. Yet this cosmic hat holds a secret far older than its elegant spiral structure. Encasing the entire galaxy is a vast, diffuse sphere of ancient stars, a stellar halo of staggering proportions. These are not the young, metal-rich stars of the bright disk, but aging suns, impoverished in heavy elements, drifting in a sparse cloud that extends for hundreds of thousands of light years. This halo is a galactic fossil record, and its composition tells a story of a violent and chaotic youth. The stars in this halo are significantly older and chemically distinct from those in the main disk, suggesting they were not born here but were acquired. Each of these ancient suns is a celestial refugee, the remnant of a smaller galaxy that was torn apart and consumed by the growing Sombrero billions of years ago. Current models of galaxy formation struggle to reconstruct this history. The sheer extent and specific metal content of the halo point to a past filled with multiple, significant accretion events, a series of galactic mergers that current simulations have a hard time reproducing. How could such a graceful and symmetrical disk survive such a tumultuous assembly process? It seems the serene beauty of the Sombrero Galaxy is a cosmic illusion, masking a history of cannibalism on an epic scale. Even as galaxies merge and stars are born, raw material for creation is still raining down from the void. Throughout the Virgo Cluster, astronomers have detected immense, fast-moving clouds of cool hydrogen gas, structures so vast they dwarf entire galaxies yet remain completely invisible to the human eye. These are the high-velocity clouds, and they are plummeting toward the cluster's heart at speeds of millions of miles per hour. Their existence is a double mystery. Where did this colossal reservoir of primordial fuel come from, and how does it survive the intensely hostile environment of the cluster itself? One compelling theory points to a violent origin. As galaxies swing past each other in the dense cluster, their gravitational interactions can stretch and tear long streamers of gas from their outer disks. This tidal debris flung out into intergalactic space could condense into the massive clouds we observe. It is a form of cosmic recycling on an epic scale. The alternative is even more profound. Perhaps these clouds are not debris at all, but pristine relics from the early universe, vast pockets of the original gas cloud that formed the supercluster, now finally succumbing to the cluster's immense gravity. This would be gas that has never been inside a galaxy, never been cycled through a star, a perfectly pure sample of the universe's primordial building blocks. Yet this leads to an even greater puzzle. The interior of the Virgo cluster is a turbulent ocean of superheated plasma, with temperatures soaring to millions of degrees. Any cloud of cool, neutral hydrogen falling into this maelstrom should be shredded and vaporized almost instantly, like a snowball thrown into a blast furnace. The fact that these clouds remain intact suggests they are far more massive and dense than they appear, perhaps shielded by their own powerful magnetic fields or stabilized by a subtle, unseen component of dark matter that holds them together. These silent, incoming giants represent a hidden chapter in the life cycle of a galaxy cluster, a continuous inflow of fresh fuel that could one day spark the birth of new stars and shape the future evolution of the entire cluster. They are a reminder that even the largest structures in the cosmos are still under construction, fed by rivers of cold gas flowing from the cosmic dark. The violence of a galactic collision can forge entirely new worlds from the wreckage. When two massive galaxies swing past each other in a gravitational dance, they do not merely merge, they fling colossal streams of stars and gas into the void. From this expelled debris, new galaxies can coalesce, born not from the pristine gas of the early universe, but from the recycled material of their parents. These are tidal dwarf galaxies, and their existence presents a fascinating challenge to our cosmic rulebook. According to our standard model, a galaxy cannot form or hold itself together without the immense, invisible gravitational anchor of a dark matter halo. This dark matter acts as a cosmic glue, providing the extra gravity needed to bind stars and gas together against their own internal motions. Tidal dwarf galaxies, however, seem to break this fundamental rule. They are formed from the visible matter, the stars and gas, that was ripped from the outer disks of their parent galaxies. Since dark matter halos are far more spread out and diffuse than the visible disks, the gravitational tides that pull out the gas and stars largely leave the dark matter behind. The result is a new galaxy that is, in theory, made almost entirely of normal baryonic matter. Observations are now beginning to support this radical idea. Studies of several tidal dwarf galaxies within the Virgo Supercluster show that their motions can be explained by the gravity of their visible stars and gas alone, with little to no need for any dark matter component. This is a profound finding. It suggests that under the right conditions, gravity alone can gather recycled material into a stable, long-lived structure without the help of the invisible scaffolding we thought was mandatory. How do these dark matter-free galaxies survive? Their stability might come from their initial conditions, born with such a placid, ordered state of motion that they can hold their shape for billions of years without flying apart. The existence of tidal dwarf galaxies forces a critical distinction in our understanding of cosmic structure. It proves that there are at least two pathways to galaxy formation: the primordial path, which requires dark matter, and this recycled tidal path, which may not. Each of these cosmic orphans is a natural experiment, testing the very laws of gravity and the role of the unseen in the architecture of the universe. Deep within the heart of the Great Coma Cluster, another gravitational titan sleeps. The galaxy NGC 4889 appears as a calm, featureless giant, a typical elliptical galaxy containing 1 trillion stars. Yet at its silent core lies a supermassive black hole of almost incomprehensible scale, a cosmic engine whose mass has been measured at 21 billion times that of our own Sun. This is not merely a large black hole, it is a behemoth that pushes the very limits of what we thought was physically possible. The existence of such a monster so early in the universe's history presents a monumental puzzle for astrophysicists. How could an object this massive accumulate so much material in the relatively short time available after the Big Bang? Our best models for black hole growth have a speed limit. As a black hole feeds, the infalling gas compresses and heats up, emitting intense radiation. This radiation creates enormous outward pressure, which actively pushes away the surrounding gas and dust, effectively shutting off the black hole's own food supply. This self-regulating process, known as Eddington limited accretion, dictates a maximum sustainable rate of growth. For a black hole to reach the mass of the one in NGC 4889, it would have needed to feed at or very near this theoretical limit for nearly its entire existence, a feat that seems incredibly unlikely given the turbulent and stop-start nature of cosmic evolution. So how did it break the rules? One compelling theory suggests it did not grow slowly and steadily, but in a series of colossal, violent feasts. In the dense, chaotic environment of the early Coma cluster, NGC 4889 may have gorged itself on entire galaxies, each merger funneling vast reservoirs of gas directly toward its core, allowing for brief, explosive periods of super-Eddington accretion. Another, more radical idea posits that the seeds for such black holes were not formed from the collapse of single massive stars, but were born large, collapsing directly from gigantic clouds of primordial gas into black holes weighing thousands of solar masses from their very first moment. This massive head start would have allowed them to grow into the titans we see today within the cosmic time frame. The silent giant in NGC 4889 is not just a record holder, it is a stopwatch. Its immense mass challenges the timeline of our universe, forcing us to reconsider the ferocity of the early cosmos and the extreme physics that govern the birth of its largest structures. Our cosmic maps reveal another layer of profound mystery in the architecture of giant galaxies. Look at a titan like Centaurus A, a galaxy 12 million light-years away, and you will find a swarm of smaller satellite galaxies orbiting around it, much like moons around a planet. But these moons are not scattered randomly in a vast spherical cloud as our best models predict. Instead, they are arranged with uncanny precision, orbiting in a single, razor-thin plane that looks more like a cosmic ring than a dispersed halo. This is not a unique quirk. We see this same strange alignment around our own Milky Way and the Great Andromeda Galaxy. The satellites are all moving within the same flattened disk, a configuration so orderly it defies the odds. Why is this so perplexing? The standard model of cosmology, which includes dark matter, tells a specific story about how galaxies form. In this story, the immense halo of dark matter surrounding a large galaxy should be roughly spherical. Smaller clumps of dark matter, which host the satellite galaxies, should be pulled in from all directions over billions of years, resulting in a swarm of satellites orbiting in every possible plane, a chaotic and isotropic distribution. The reality of these thin, rotating planes is a direct statistical contradiction. It would be like tossing 100 coins into the air and having every single one land perfectly on its edge. The probability is so vanishingly small that it forces us to question the very foundations of our model. What does this mean for our understanding of dark matter? It suggests that the substructure of dark matter halos might be far more organized than we ever thought, perhaps forming in vast, disk-like sheets itself. Alternatively, it could point to a different genesis story for these satellites. Perhaps they were not all captured individually, but were born together from a single, massive ribbon of gas that was torn apart during an ancient galactic collision. This would explain their shared orbital plane, but it would require a rewriting of satellite formation history. The silent, coordinated dance of these satellite galaxies is a subtle but powerful clue. It implies that the rules governing the assembly of the largest structures in our supercluster may involve a level of order and coherence that our current physics has yet to capture. Even the most fundamental constants of our universe are now being questioned. At the very heart of modern cosmology lies a number so critical we use it to gauge the size, age, and ultimate fate of everything we see. This is the Hubble constant, the rate at which the universe is expanding. For decades, we believed we were honing in on its true value, but a disturbing schism has emerged, a direct conflict between two of our most trusted methods of measurement. One path uses the universe as it is today. Astronomers observe pulsating stars called Cepheid variables in galaxies throughout the Virgo Supercluster and beyond. These stars have a known relationship between their pulse rate and their true brightness. By measuring how bright they appear from Earth and comparing it to their known true brightness, we can calculate their distance with remarkable precision. Combine this with measurements of how fast those galaxies are moving away from us, and you get one value for the Hubble constant. The other path uses the universe as it was in its infancy by studying the cosmic microwave background, the faint afterglow of the Big Bang. This ancient light carries a precise imprint of the young cosmos, and by applying our well-tested model of the universe's evolution, we can predict what the expansion rate should be today. These two methods, one a local measurement and the other a fossil relic, should converge on the same number. They do not. The discrepancy is not a small rounding error. It is a significant and stubborn gap that has only grown with more precise observations. The local universe, measured with Cepheids, appears to be expanding faster than the pristine early universe, as measured by the cosmic microwave background, says it should be. This is the Hubble constant tension, and it represents a full-blown crisis in cosmology. It suggests a flaw in our understanding, a crack in the foundation of our cosmic model. Could there be an unknown source of energy in the universe's history that gave expansion an extra kick? Or is dark energy itself not constant but evolving and strengthening over time? Perhaps the most radical possibility is that we are seeing evidence for entirely new types of subatomic particles or forces that altered the early universe in ways our models do not account for. This is not just a debate over a number, it is a direct challenge to the standard model of cosmology, implying that our story of the universe from the first second to the present day is missing a crucial chapter. The tension is a ghost in the data, a whisper from the cosmos that our most fundamental assumptions about reality may need a profound rewrite. The mystery of dark matter deepens with every experiment that comes up empty. For decades, the leading hypothesis has been that dark matter consists of weakly interacting massive particles, or WIMP. These theoretical particles are thought to be heavy, slow-moving, and only rarely bump into normal matter. To find them, scientists have built extraordinarily sensitive detectors, placing them deep underground in old mines and beneath mountains to shield them from the constant rain of cosmic radiation. These laboratories are the quietest places on Earth, listening for the faintest whisper of a WIMP colliding with an atom. Yet after years of searching, the detectors have heard nothing. This profound silence is forcing a major shift in our thinking. If WIMP are not the answer, then what is? The search is now turning toward more exotic and elusive possibilities. One compelling candidate is the action, a hypothetical particle that is billions of times lighter than a WIMP. If actions exist, they would be incredibly abundant, forming a cold, wavy ocean throughout the cosmos. They would hardly interact with normal matter at all, which explains why we have not found them, but their collective gravitational influence would be enough to shape the entire supercluster. Detecting them requires a different approach entirely, using powerful magnetic fields to try and convert these ghostly particles into faint microwave photons. Another, more dramatic idea is that dark matter is not a sea of particles, but a population of ancient black holes. These would not be the black holes formed from dying stars, but primordial black holes created in the first chaotic second after the Big Bang from ultra-dense knots in the fabric of space-time. They could range in size from a small asteroid to a giant planet, and they would be completely dark, betraying their presence only through their gravity. The ongoing search for these primordial black holes involves watching for moments when one passes in front of a distant star, its gravity briefly bending the starlight and causing a telltale flicker. The continued failure to find a definitive signal is in itself a powerful piece of data. It tells us that dark matter is even more alien and detached from our world than we imagined. Its dominance over the supercluster's structure is absolute, yet it remains a ghost, a cosmic architect that leaves no fingerprints at the scene of the crime. The Great Attractor's pull may not be its own. New observations from radio telescopes like Parkes are revealing a startling possibility that this colossal anomaly is not a final destination but merely a waypoint. The motion we observe of our Milky Way and thousands of other galaxies appears to be part of a far grander river of galaxies, all flowing toward an even more immense and distant structure, the Shapley Supercluster. This is a gravitational watershed on a scale we are only beginning to comprehend. The Shapley Supercluster is the most massive known concentration of matter in our observable universe, a dense knot in the cosmic web containing tens of thousands of galaxies. The gravitational pull from this distant titan is so immense that it seems to be orchestrating the motion of galaxies across hundreds of millions of light years, including the apparent pull of the Great Attractor itself. This reframes the entire mystery. The Great Attractor is no longer just a single, unseen mass hidden behind the dust of our own galaxy. It is now a local concentration within a vast cosmic current, a ripple in space-time caused by a distant mountain of matter. So the question shifts. We no longer ask only what the Great Attractor is, but what role it plays in this larger gravitational symphony. Is it a dense cluster amplifying the pull from Shapley, or is it a separate structure whose own gravity simply aligns with this greater flow? This deeper layer of the mystery reveals that the forces shaping our corner of the universe are more interconnected and far-reaching than we ever dreamed, pulling us toward a truth hidden behind not one veil but many. Our local cosmic neighborhood is also caught in this immense flow. The Milky Way, Andromeda, and about 80 other smaller galaxies form a gravitationally bound family known as the local group. For now, we are a small, isolated archipelago in the vast ocean of space, but our isolation is temporary. The entire local group is falling, slowly and irrevocably, toward the gravitational heart of the Virgo Supercluster, the Virgo Cluster itself. This is a journey that will take many billions of years, a cosmic dance that has already begun. The first act is a local merger. In approximately 4.5 billion years, our Milky Way and the Andromeda Galaxy will collide. They will swing past each other, their gravitational forces stretching long tidal tails of stars into the void before swinging back to merge completely. The result will not be a grand spiral, but a large, amorphous elliptical galaxy, which some astronomers have nicknamed Milkomda. This new galaxy will be the core of our future local family. But the dance does not end there. As Milkomda forms, the entire local group will continue its slow fall toward the Virgo Cluster. Over tens of billions of years, this nascent giant and all its satellite galaxies will be drawn into the cluster's dense core. What happens then is a matter of intense speculation. Will Milkomda survive as a distinct entity for a time, orbiting the cluster center like a giant moon? Or will it be quickly torn apart by close encounters with other massive galaxies, its stars scattered and assimilated into the cluster's central giant, Messier 87? The final state is predicted to be a single, colossal elliptical galaxy, a behemoth formed from the merger of hundreds of galaxies, including our own. This ultimate fate raises profound questions we cannot yet answer. What will the night sky look like from a planet orbiting a star in that future galaxy? It would be a sky permanently alight, filled with the blended glow of trillions of stars with no true darkness left. And what of the vast reservoirs of hydrogen gas that currently float between our galaxies? Will they ignite in a final, glorious burst of star formation as they are compressed during the merger? Or will they be heated to such extreme temperatures by the violent interactions that they simply glow, invisible to any future eyes? This cosmic endgame is written in gravity, but its precise choreography remains one of the supercluster's longest and most patient mysteries. These colossal structures force us to confront the very bedrock of modern cosmology, the cosmological principle itself. This principle is a grand and simple assumption that on the largest scales, the universe is both homogeneous and isotropic. Homogeneous means the matter is spread evenly, like the particles in a perfectly mixed batter. Isotropic means it looks the same in every direction, with no special center or edge. This idea is not just a philosophical preference, it is the essential starting point for almost every equation describing the Big Bang and the evolution of the cosmos. Yet the Virgo Supercluster, a structure spanning over 100 million light-years, stands as a direct challenge. It is not a smooth, uniform distribution. It is a specific, complex architecture of clusters, filaments, and vast voids, a distinct continent in the cosmic ocean, and it is not even the largest. Far beyond it lies the Hercules Corona Borealis Great Wall, a colossal filament of galaxies so immense it stretches for 10 billion light-years, a structure that seems to defy the very meaning of the phrase large scale. How can the universe be considered smooth and featureless when it contains such gargantuan, organized formations? The principle begins to fray at the edges. Perhaps our definition of large scale is still too small. Maybe we need to zoom out even further, to scales so vast that even these great walls appear as mere granules in a truly uniform background. But with each new map of the cosmos, the largest structures we can see continue to push the boundaries of what is considered possible under the principle. This is not a minor detail, it is a fundamental tremor. If the cosmological principle is not perfectly true, then the foundation of our entire cosmic model requires a subtle but profound adjustment. We are left gazing at the map of our supercluster, wondering if the universe's ultimate blueprint is far more complex and textured than we ever dared to assume. These cosmic questions will not remain unanswered forever. A new generation of eyes is turning toward the sky, instruments of such power they promise to illuminate the supercluster's darkest corners. The James Webb Space Telescope, with its infrared gaze, peers through the obscuring dust of the zone of avoidance, finally revealing the true nature of the Great Attractor. It will dissect the ancient starlight in galactic halos like the one around the Sombrero Galaxy, reading their chemical histories with such precision we can reconstruct the exact sequence of mergers that built them. Meanwhile, the Vera C. Rubin Observatory will conduct the ultimate cosmic survey, scanning the entire sky every few nights. Its relentless watch will catch the subtle flickers of distant stars, hunting for the invisible mass of primordial black holes. It will map the faintest outer stars of galaxies like Messier 87 in unprecedented detail, tracing the true shape and density of their dark matter halos and putting our theories of invisible structure to the ultimate test. And then there is the Square Kilometre Array, a radio telescope of almost unimaginable sensitivity. It will listen for the faint whispers of cold hydrogen gas in the vast intergalactic voids, finally finding the universe's missing baryons. It will map the high-velocity clouds falling into the Virgo cluster in stunning resolution, watching them survive their plunge into the hot plasma. It will even detect the faintest echoes of fast radio bursts, pinpointing their locations with such accuracy that we can finally identify the exotic engines that power them. These are not just new tools, they are keys designed for specific locks. Each mystery we have encountered, from the ghostly galaxies devoid of dark matter to the perplexing plains of satellite galaxies, presents a unique signature that these observatories are built to capture. They will transform our ghostly maps of the supercluster into a dynamic, living portrait, revealing not just what is there, but how it moves, evolves, and interacts. The coming decade will be a golden age of cosmic discovery, where the shadows we have been staring at for so long will finally step into the light. From the hidden force pulling our galaxy to the silent, coordinated dance of satellite galaxies, our journey through 25 cosmic mysteries reveals a universe far stranger and more wonderful than we ever imagined. The Virgo Supercluster is not merely a collection of stars and galaxies. It is a living, breathing cosmic laboratory, a testing ground where the fundamental laws of physics are both proven and challenged with every new discovery. Each phenomenon we have explored, from the ghostly dark matter halos to the impossibly massive black holes, represents a frontier of human knowledge. These are not just isolated curiosities, they are interconnected puzzles, pieces of a grand cosmic picture we are only just beginning to assemble. They push the boundaries of our understanding, forcing us to question our most basic assumptions about reality, gravity, and the very fabric of space and time. This relentless pursuit of answers, this drive to map the darkness and decode the whispers of the cosmos, is one of humanity's most profound endeavors. It connects us to every person who has ever looked up at the night sky in wonder. So, as we conclude this voyage, we turn the question over to you. Which of these 25 unexplained phenomena captured your imagination the most? Was it the galaxy made almost entirely of dark matter, or the perfect cosmic bullseye of Hoag's object? Share your thoughts in the comments below. The greatest mystery of all may be our own unending quest to find our place within this vast and enigmatic supercluster we call home. Our own supercluster is but a single leaf in a much larger cosmic forest. The Virgo Supercluster, with all its immense clusters and voids, is actually just one component of an even grander structure known as the Laniakea Supercluster. Laniakea, a Hawaiian word meaning immense heaven, is a breathtakingly vast gravitational watershed. It encompasses our local supercluster along with countless others, a sprawling continent of galaxies spanning over 500 million light-years. Within this domain, every galaxy, including our own, is flowing along invisible rivers of gravity toward a central point known as the Great Attractor, the same mysterious focal point we discussed earlier. This reveals its true nature not as a lone anomaly, but as the gravitational heart of our entire supercluster continent. Yet even Laniakea is not the final word. It is merely one node in the largest known structure in existence, the cosmic web. This is the ultimate architecture of the universe, a spiderweb of glittering galaxy filaments separated by unimaginably vast dark voids. Our entire journey through 25 mysteries has taken place within a single, small neighborhood of this infinite tapestry. What lies beyond the next filament or the next? The scale is so immense it defies human comprehension, hinting at mysteries and structures so grand we lack even the language to describe them. Our map of the cosmos is still being drawn, and with every new line we trace, the universe reveals a deeper, more magnificent unknown.